Very good afternoon, everyone. Welcome to this problem solving session. It's our week 2, and we'll cover today problems based on whatever you have learned in the previous week. So specifically, I will be going through transfer function, problems based on transfer function, and also what are poles and zeros, what are the effect of poles, then what is stability, in particular what is BIBO stability, and we'll see some problems based on that as well, like BIBO stable, when a system is BIBO stable, or in general, what is stability, etc., etc. Okay, so I hope you have gone through the contents of previous week, but still I'll just summarize or just define what is transfer function. So what is transfer function? It's actually defined as the Laplace transform of the output to the Laplace transform of input, assuming all zero initial conditions. So this is very important. So this is very important. In transfer function, whenever you define transfer function, normally students, they say it's a Laplace transform of output to the input, but they ignore this thing, and it's very, very important to say this thing. We'll see in a while in some problems. So this transfer function, you might have studied this in detail just for this recap purpose, and we'll be doing questions to get you on track and just defined it, or we write transfer function sometimes with G of S, sometimes with H of S. It's given as Laplace transform of output to the Laplace transform of input with zero initial conditions. Okay, so this is it. And there is another definition we'll see in the later, well, when we do the questions based on that. That is, it's actually the Laplace transform of impulse response. The transfer function is actually Laplace transform of impulse response. So if you need to find transfer function and you're given an impulse response, just take Laplace transform of that. Similarly, if you're given a transfer function and you need to find impulse response, just take inverse Laplace of that. I will see later on in detail. As of now, let's just start with this question. Right, this is our question number 1. You can see on your screen the transfer function of the electrical system shown in figure 2 with EI as the input and EO as the output is. So basically we have been given a circuit where we are being asked to find the transfer function. Okay, so as I said, the transfer function is the Laplace transform of output to the Laplace transform of input. So this we have to find. Okay, so let's, and these are the options that are given. So see, one important thing here, we have R1, C1, R2, C2, and R2 and C2 are in parallel, and R1 and C1 are in series. So we can write the impedance of this C2 and C1 as like this. So ZC1 will be equal to 1 by SC1. Similarly, ZC2 will be 1 divided by SC2. Correct? So these are the impedances of C1 and C2. Then what we will do, basically, when we have to find this, we will just simplify this circuit first, and then we can use voltage division rule to find output voltage in terms of input voltage, and then take the ratio of output over input, and that's our transfer function. Okay, so I'm going slow for this question number one because not many people have joined, and I'm assuming other people will join in the meantime. Right, so let's do one thing. Let's just evaluate the net uh, like impedance of this RC pair, equivalent impedance. So we can just write it here. Solution: the equivalent impedance of parallel R2 C2 pair is given by. That will be, I'm just denoting it with Z equivalent, which will be given by C. Parallel combination will be R2 into 1 by SC2 divided by R2 plus, so in general it's ZC2, right? So you can write it like this: R2 into ZC2 divided by R2 plus ZC2, correct? So now let's put in the value of ZC2. It will be R2 into 1 by SC2 divided by R2 plus 1 by SC2, correct? If you simplify it, we'll get Z equivalent as R2 divided by 1 plus SC2 R2. I did nothing, just did cross multiplication here. And then you can see SC2 and SC2 will vanish, and we'll get this as Z equivalent. So this is our Z equivalent. It's the equivalent impedance of the parallel pair of R2 and C2. So we have a circuit like this now. So you have something here, then you have something here. Right, so let's make it like this to avoid confusion. This is our Z equivalent. This whole is our Z1. I think I've denoted it with Z1. Yeah, ZC1. No, yeah, let's keep it as Z1, and it is ZC1, and this is R1. Okay, now we have to find, so this is my output voltages across this R1 C1 pair, and input voltage is this. So here we have EI, and here this whole we have E naught. Now tell me, voltage using voltage division rule, my E naught will be, right? So using voltage division rule, my E naught of S, it will be equal to this R1 plus ZC1 into EI is divided by R1 plus ZC1 plus Z equivalent. I'll just explain you here. So if you have two resistances, for example, this is your VI, this is your V output, this is your R1, this is your R2. If you have to find this VR2, so this V naught here, this will be given by V naught is R2 into VI divided by R1 plus R2. I hope you are well aware of this voltage division rule. Same rule I applied here. So I got this thing. Now I'll just put in the value of ZC1, then also I'll put the value of Z equivalent, right? So just erase this here. Now let's put in the values. So we have E naught of S. Then I will bring this EI of S here. This is my transfer function, which is actually needed. And it is equal to R1 plus ZC1 is 1 by SC1, then divided by R1 plus 1 by SC1 plus Z equivalent is what? R2, 1 plus SC2 R2. You have to be very careful because you get sometimes similar questions in GATE as well. So you have to be very careful with the multiplication stuff here. So let's multiply this part here because it's in the numerator as well as denominator. So what will be the multiplication of this part? R1 plus 1 divided by SC1, it will be R1 SC1 plus 1 divided by SC1. Okay, I'll just put it there, this value. So what I will get, this is in the numerator as well as denominator. So I'll write it like this: 1 plus SC1 R1 divided by SC1. Then denominator, same thing, 1 plus SC1 R1 divided by SC1 plus R2 divided by 1 plus SC2 R2. Just give me a minute. Just okay. So now let's just simplify it again. Just simplify this denominator now. So it will be equal to 1 plus, this is numerator, I'm writing numerator first, SC1. Now let's take into consideration denominator. Multiply this thing first. So it will be 1 plus SC1 R1 into 1 plus SC2 R2, then plus R2 SC1, then divided by SC1 into 1 plus SC2 R2. This SC1 and this SC1 goes. What you will be required with, it will be 1 plus SC1 R1 divided by 1, and I'll just take it above. It will be the reciprocal of it. So it will be 1 plus SC2R2 divided by 1 plus SC1R1 into 1 plus SC2R2. And this is the required answer. No, there is another thing, plus R2SC1. Now let's check in the answers. This one matches. If you see R1C1S plus 1, R2C2S plus 1 divided by this thing. So this is the correct answer. I'll just recap what I've done. I was given a question. The circuit was given. I had to find the transfer function of this circuit. And what is the approach? Approach is you have to see the relationship of the Laplace transform of output over input. So this we needed to find, right? And for that, we just have to simplify circuits. Whenever you get a circuit and you have to find the transfer function, simplify the circuit simplify that in a very like if it is possible to simplify that, try to, because then things will be very easy, and then at the last try using voltage division and you'll get the answer. Or otherwise you will have to use Kirchhoff's laws, Kirchhoff's current law, Kirchhoff's voltage law, then try to equate stuff and then get the relationship between output and input, right? So this way, this was a very simple question where you just had to, do parallel combination of R2 and C2. The only trick was you cannot you cannot directly use this C2. You have to write it in terms of its impedance, which is 1 by SC1, right? Similarly, if it is inductance, if there was an inductor L, then you will write S into L. So it actually comes from this Laplace transform, right? So this is it. This was your question number 1. Now let's move to question number 2. Okay, so read the question. The question is, you're given a simple automobile suspension system as shown in figure 1, right? And then you have to find the transfer function. So whenever you have to find the transfer function, it will be specified what you have to take as input and what you have to take as output. So it's everything is given. You have given a spring mass damper system, and then you have to find the transfer function with x1 at point P as the input and output as the vertical motion x naught. So basically you have to use Newton's laws here. Just apply Newton's second law, force balance equation, and then try to get input at one side and output at another one, and then just take something common and you'll get the answer, right? So if we apply, let's solve it first. I'll just take a fresh page. Okay, so let's try to solve it. Right, so if you apply Newton's laws here, so you have, this is m mass, so you will write m dt d2x by dt square. This is xo. Then damper, whenever you have a damper, see, you have a spring here, and the force exerted, or when you stretch it or compress it, what is the force that you have is k into x. K is the spring constant, and x is the displacement. Similarly, if you have a damper B, then you have B into dx by dt. Whenever you have a spring, you have learned it, or you must have gone through. If you have gone through the lectures, you must be aware of this thing. So if you have a spring, your force will be kx, and if you have a damper, your force will be B dx over dt. Right? So now apply similar stuff here. So you have the force due to this mass, that's m d2 x naught over dt squared, plus now you have a damper. So you will have B, then d by dt of x naught minus xi, because this damper, it's connected with, like, it has both effects, x1 and x2. Right? So x1, x2, sorry, x naught effect is coming from here, and similarly x1 effect is coming from here. Then you also have spring k into x naught minus xi, and due to Newton's second law, this will be equal to 0. So I'll just write it here. M x naught double dot plus b x naught dot minus xi dot plus k into x naught minus xi is equal to 0. I did nothing. I just applied Newton's second law. I'll just write it. You just recap if you are not familiar with this, Newton's second law, and how to apply it on systems where there are two displacements or whatever is there, you just have to make sure that you take the effect of both. Okay, so now this is in time domain, and you have to find transfer function. Transfer function is an S domain. So first thing is we have to take Laplace transform, right? So the other step is what I'll do, I'll take x naught on one side and xi on the other side. I'll do this, or mx double dot of x naught plus bx naught dot plus kx naught is equal to bxi dot minus plus kxi. So I just rearranged it. Now I will take the Laplace transform again. So whenever, as I defined earlier, whenever we are saying transfer function, we assume all initial conditions to be 0. So when I take Laplace of dx by dt, so I will assume all initial conditions to be 0. So in that case, what will this be? It will be m into s square xs x naught of s plus b into s into x naught of s. Similarly, k into x out of x naught of s, right? This is equal to b into s into xi of s plus k into xi of s. I'm just denoting Laplace transform variables with the capital letters. Now let's see what we can take common. We can take x naught common from LHS and xi common from RHS. So we will get x naught of s into ms square plus bs plus k is equal to xi of s. You have bs plus k. Okay, now you'll get the transfer function, that is x naught of s over xi of s. That will be equal to bs plus k divided by ms square plus bs plus k. Okay, so which option is the correct option? Now tell me which option is the correct option. Anyone?
B option, sir.
Okay, so B option is the correct option. I will again just explain it. See, force is, so this is some force is acting on here, which displaces this mass, which displaces this point P2, like you get a displacement of xi, right? Uh, then this mass, which this mass is also displaced vertically by x naught. You have a damper, you have x, you have to see the effect. Like basically you have to make a free body diagram and then just simplify the system. You'll get some expression, take in time domain, just take Laplace transform of that. You'll get something you will get the relationship between input and output, and then you know the transfer function is Laplace transform of output over input. Just rearrange and you'll get the answer. So it's very simple. It's not rocket science here, but you just have to analyze. Otherwise, at the first look, this question will look very difficult because you have something very like fancy here, but it doesn't like after carefully looking at it, it's a very easy question. Right now, if you have understood the previous question, try solving this question and tell me the answer. So you have a simple mass spring friction system as given in the figure. where K1, K2 are spring stiffness, right? F is the friction, M is the mass, F is the force, X is the displacement. Basically, you have this mass M, you have this mass M, you are applying a force F on this mass, so this mass will be displaced by the displacement like by a distance of X, so that X is the displacement. Then what will happen? So there is this force acting on the spring as well, then the spring will revert in this direction. Similarly, this there is a force acting on this spring from this side, so it will respond in this direction. There is a friction force, and friction is modeled as a damper. So you can assume here to be a damper. So it's a mass spring damper system. So this friction is modeled as a damper. So wherever there is friction, you can assume there is a damper, right? So you have a damper. So whenever I have to take the effect of K1 or K, it will be Kx. And if it is F, it will be F dx over dt because it's acting as a damper, right? Then you have mass, you know that is d2x over dt squared, and F is the force. So just apply force balance here and tell me the answer. I'll just simplify it for you. So F, I'm applying force F, and that force will be equal to force on mass, that's m d2x by dt squared, plus I told you there is a damper due to spring, so it will be F dx by dt. Now this is important. You have two springs. You have two springs. Right? So you have two springs, and you'll write k1 of x plus k2 of x, right? And after this, just take Laplace. So when you take Laplace, you'll get f of s m s square xs f into xs, sorry, f into sxs plus k1 plus k2 into xs. Now the transfer function in this case will be, it is given, it's given that the transfer function is xs over fs. So now tell me the answer. What will be xs over fs? It will be, fs is 1, no sorry, xs over fs, yes, what it will be, 1 divided by ms square plus fs plus k1 by k1 plus k2, as simple as that. Is there any option that matches? Yes, this option, right? So you just have to be very careful with Newton's laws. Just to recap those laws, and just have to apply them, take Laplace, take the relationship. It must be defined in the question. What you have to take as input, what you have to take as output. Otherwise, it will be quite obvious what's input and what's not. Now, try solving this question, or before this question, solve this question. This is relevant. This is relevant. So you have to find the transfer function of this system. It's similar to what you solved in question number 1. Now here you should be able to tell me the answer. Transfer function will be, it's given, V naught of S over Vi of S. So you find V naught. What is V naught? V naught is the, okay, I'll just simplify it for you. V naught is the voltage across capacitor C2, C, and Vi is the input excitation. Now solve it. Solve it and tell me the answer. Anyone? Yes, anyone? Okay, I'll just solve it for you. Just apply KVL. So by KVL, Kirchhoff's voltage law, very simple. What is VI? VI will be, okay, let's assume there's current I that's flowing in the circuit. So VI is RI. I'll just make it clear so it's in time domain. RIT plus V naught. Okay, so that's it. This is KVL. Now what I have to do, I have to find transfer function, and for that I need to take Laplace. So now I have V out here, I have V in here, but there is this problem which is created by Ri, right? So somehow either we have to put in, we have to find the value of this V output in terms of Vi, in terms of I, or we just have to find the value of Vi and then the value of Vo, then take Laplace, then divide them. That's it. So we find the value of Vi, it's in terms of Vo. Now we'll also find the value of Vo. And what is Vo? Vo is the voltage across the capacitor C, and the value, its value would be 1 by C integration of I dt. Right? You know the voltage across a capacitor is 1 by C I dt. Now, what we have to find? We have to find V naught of S over Vi of S. Okay, this we need to find. But we are given things in time domain, so we will take Laplace transform of both. So let's take Laplace transform of Vo first. So Laplace transform of VOS is 1 by C. I told you the integration. So the Laplace transform of d by dt of dx by dt is s into x. Similarly, Laplace transform of st is x by s. We have studied it. So it will be 1 by sc, right? 1 by SC of I of S. Now, let's find the Laplace transform of Vi of S. Vi, which is Vi of S, that is R into I of S, plus we know Vo is 1 by SC I of S, which is equal to R plus 1 by SC into I of S. Just multiply this Vi and Vo, you will get the answer. So Vo is 1 by SC divided by Vi is of I of S, and Vi is R plus 1 by SC I of S. This I and this stands cancelled, and this is the answer. 1 by SC divided by 1 plus R divided by R plus 1 by SC, right? So there are different ways to solve. This is one of the ways. This is a very simple question. Everybody of you should be able to solve this, because this is what we have been doing. We had a circuit, we needed to find this equation first, then find the Laplace transform and get the solution. But in this question, we are directly given a differential equation, and we are asked to find xs over us. Xs over us. Please try, everyone. It's very simple. Anyone? Tell me the answer.
Sir, first option.
This one?
Yes.
Can you cross check?
The second option.
This one?
Yes, sir.
Which one? This is the correct answer. So just I know the mistake which the first guy has made. I'll just explain. See, transfer function questions are very easy if it's given in terms of this. You're given a differential equation. Otherwise, you have to derive this differential equation from the model. So 6x plus 3xt 10 ut. Now take Laplace. This will be s squared xs. You have to assume zero initial conditions because you are doing transfer function. 6s into xs plus 3 into xs equal to. Now here the person who gave answer as option A has done ut is 1 by s, right? But you need not put that. The transfer function is output over input, and you're putting the value of the input. As of now, you have to find the transfer function, not putting in the value. You found the value of output y of s, not the transfer function. Now take xs as common. So it will be s squared plus 6s plus 3 into xs, 10 into us, then output over input, or xs over a. That's what was required. It's given by 10 over s squared plus 6s plus 3. Very simple. Now we have this question. we have this question. Can anybody solve it? It's very conceptual, but very easy at the same time. If the transfer function of a system is given by, so you are given a transfer function g of s, which is equal to 1 divided by s square plus as plus b. And you are also given where a and b, they are not equal to 0, and one of the poles of the system is poles. Poles means, so it means the value of s. So it's a second order system. There will be two poles. One of the poles, let's say that is s1, that is given as minus 4 plus 7i. Right? Then what are a and b? We have to find the value of a comma b. It's a very tricky question and answer in 2 lines. So I'll just give you a hint. Answer me. You are given a second order system. It means the number of poles will be 2. Right? So the number of poles will be 2 because the highest power of s is square. So it means 2 poles are there. One pole is given here. So can anybody guess the other pole, s2? Can anybody guess the other pole?
-4 -7i.
Very good. So -4 -7i. Why? Because complex poles or they occur in pairs. Right. So if it is -4 plus 7i, the other will be -4 minus 7i. So then it means we can write this as s square plus as plus b. We can write it as s plus 4 minus 7i into s plus 4 plus 7i. Correct? Because there are two poles, it means when you put this equal to 0, you will get the first pole. If you put this equal to 0, you'll get the second pole. So I just wrote it like this. And if you simplify, you'll get this, the first term. So let's simplify it. What we will get? We will get s square plus 4s plus 7s into iota plus, or we'll do it other way. Okay, we can do this way as well, but it will be a bit complicated. Anyhow, let's do it. It will be 4s plus 16 plus 28i minus 7i into s minus 28i minus plus 49. This and this goes. This and this goes. So we have this equal to s square plus 8s plus 4s plus 4s. We have 49 plus 16, 65. Now this we will compare with s square plus as plus b. So it means our a is 8, our b is 65. So the option number, this is the correct answer. Okay, so very simple. You just have to catch the concept. So you get sometimes similar 1 marks questions in GATE where you are given. Yes. If somebody has a question, please.
So
Please
that,
unmute yourself and ask.
So that pole 1 -4 -7. Can you repeat that?
Okay. So you are given in the question that you have a system transfer function which is given by this. It's not given directly, it's given in terms of a and b. Then you are given that one of the poles of the system is -4 plus 7i, right? It means When you solve this denominator, you will get the value of S, and the value of, there will be two values of S because it's a second order system. The degree is 2. There will be two values. So two roots basically. It's a quadratic equation. There will be two roots, right? One root
Yes.
is given, -4 plus 7i. And what will be the other root? We have to find. So we know it's a complex root. And when it's a complex root, we know complex roots, they occur in pairs. If it is -4 plus 7i, the other root has to be -4 minus 7i because they
Yeah.
occur in pairs. It
When
means wait. It means if S is -4 plus 7i, other pole has to be -4 minus 7i. But when we write it, it is actually S minus S equal to, but I can write it like this: S plus 4 minus 7i, like this. Similarly, the other pole will be S plus 4 plus 7i equal to 0. I can write it like this.
yes.
Why? Because I just put it this side,
Yeah, the minus has
right?
come to this, to the left hand side. Minus is on the left.
Yes, but when we when we shift it to the left hand side, it will be plus, right?
Correct.
So yeah, that was your doubt?
Yeah.
Okay, okay, no problem. So you have to catch the concept. The concept here was just the complex roots, they occur in pairs. And then you see the answer is in 2 lines. So for some who don't know the concept, it will be very difficult. It will not hit them how to solve this. But if you know the concept, you'll do it in a minute or in 20 seconds, right? So this is that's why it's very important to learn the concepts. So let's move on. I hope you will now be able to solve these transfer function questions easily because there are not many and not difficult ones in your assignment. But now what is important is this stability. I'll just explain you first and then we will uh, move, like we will solve the questions. Yeah. So basically, as of now, you have not learned control in details. We are just going step by step. So as a stability can be defined, there are many notions of defining stability. We'll learn by the end of this course, when you will learn state space modeling, there you will say the system is stable if the poles or the roots or the eigenvalues of A matrix, where A is a system matrix, they are on the negative. So, but as of now, you have only learned transfer function. So in terms of transfer function, when we define stability, we make use of the poles, right? So for example, I'll take simple example. Let's assume I have a transfer function g of s is equal to s plus 1 into s plus 2. So this is my simple transfer function. And what are the poles? Poles are the roots of denominator, right? So they are the poles and they govern system stability. So these poles, they govern stability of the system. So it is these poles and their locations which decide whether a system is stable or not. And later on, when we will learn state space modeling, there we will see, oh, actually these poles correspond to the eigenvalues of system matrix. But as of now, just remember, the effect of these poles, what happens, what are the consequences of these poles, and in the next week we will see the consequences of zeros or effect of zeros. But for this week we restrict ourselves to the effect of poles, where they determine whether a system is stable or not. Now see, this is my one transfer function. Let's assume I have another transfer function which is in this form, s plus 1 square. I can write it like this: 1 divided by s plus 1 into s plus 1, right? So when there are these poles which are not coincident, where, like, see here you have one which is a coincident pole because it repeats itself. So when there are no coincident poles, those poles are called simple poles. So wherever it's mentioned, a system has two simple poles at -1 and -2, then you can write that system like this. But if it is written, otherwise it will be explicitly mentioned. If it is not a simple pole, they will repeat itself. So what is the multiplicity? What is the order that will be given? A pole of order 2 or something or something. Like here, this is S1. One is the pole of the system with order 2, right? Because it repeats itself. It repeats itself. Okay, so as of now, simple poles are those poles which are not coincident. Fine. Now, if the poles of a transfer function, they lie in the left half plane. See, this is my sigma and j omega, right? S is equal to sigma plus j omega. This is my S plane. This is my right half plane where everything is positive. See, the sigma is positive, j omega is also positive. I have this LHP. I have this LHP where the sigma is negative, j omega is a positive as well as negative if you see the downwards, right? So if my poles, basically S is a complex number, right? So here we have only the real poles, that's a different thing, but S in general is a complex number and the value of S can be complex as well, as we saw in the previous question. So if my poles, all poles actually, all poles, if they lie in left half plane like this, we have S equal to -1 and S equal to -2. If all my poles lie in the left half plane, then my system is stable, right? If any of the poles, like if I have three poles of the system and one pole lies in the RHP, so if any pole lies in RHP, that makes the system unstable. That makes the system unstable. So if we have poles on the imaginary axis, so if we have poles, imaginary axis, then system is marginally stable. That means the response is oscillatory. I'll explain that. But if I have repeated poles, mark this like point. If I have repeated poles on the imaginary axis, then my system is unstable. So for example, I have a pole at 2j, -2j, a plus 2j, and other one is at, of course, if it is a second order system, it will be at -2j. This system is marginally stable. It means the response is something like this, oscillatory, right? But if I have repeated poles, for example, I have two poles at j, then my system is unstable. Or if I have repeated poles at 0, then my system is unstable. So whenever I have repeated poles on imaginary axis, that makes my system unstable. Now, what does this mean? Stable, unstable, oscillatory, marginally stable. What does it mean? Just explaining you in simple terms. See, I have a system, transfer function, as you saw, you give some input and you get some output. So this is time and this is your output. Let's assume this is y of t. It's in time domain. So if you give some input to the system and output is like this, right? It means this output is increasing with respect to time. So eventually, as time goes to infinity, this output will go to infinity. So for example, take an example of a fan. I just turned on the fan will speed up, then it will settle at some value, and we'll get that it will rotate at that particular speed. But if it was an unstable system, then what will happen? It will speed up, speed up, speed up, and it will be so fast that it will blow. It will blow away, right? So in that case, if my system is unstable, it means its response is going to infinity. So it's going to infinity. It means it's an unstable system. So you are giving some input, but if it is an unstable system, the response, it goes to infinity. But if it is a stable system, then the response, it settles down. So if I gave some input, so it will settle down to some value, right? Or in other words, I started with here, so it will settle down, right? Or it will settle down to 0 as well, no problem in that. So my stable system that settles down to a value, right? That has a finite output. And your marginally stable system, what is that have? The output is a bit oscillatory, sort of, right? Sinusoidal. If you have a sine wave, the graph simple like that, you have an oscillatory response. Like it doesn't settle, but it oscillates between two values. So that's marginally stable. Now you have understood. Okay, when a system is stable, you just have to see the poles of the system, right? This was stability. Then what is bounded input, bounded output stability? That is also called BIBO stability, right? So BIBO stability means, and just take a page. Yeah. So BIBO stability means BIBO. It means if I give any bounded input, mark this word any. Any is very important. If I give any bounded input, I should get bounded output. Okay. So if this is the case, then my system is bounded input, bounded output stable. The criteria for a system to be bounded input, bounded output stable is that all the poles must lie strictly in the LHP, left half plane. For a system to be bounded input, bounded output stable, that means if we provide any input, the output will be bounded. The criteria is all poles must lie in the LHP, in the left half plane. Then and only we can say my system is bounded input, bounded output. If we have some inputs for which my system output is bounded, but also we have some inputs for which my system output is unbounded, then that system is not bounded. That's not BIBO stable, in short. So for BIBO stability, you must check the pole locations. All the poles should strictly be in the left half plane. If that is not the case, then your system is not bounded input, bounded output stable, right? So it's very important. Now you'll have to think when we solve some questions. You'll have to think how the system, when the system can be bounded input, bounded output stable in this case. In the following question that we'll be seeing, and it will be more clear. Let's see this question. And the transfer function part will also be clear here. See, consider the system whose governing equation is y double dot plus 4yt equal to ut, the input for which the system output would be unbounded is. So indirectly, it is saying, so first of all, when the system output will be unbounded, it means the system should be unstable. Right? The system should be unstable, or if it is unbounded, it means not all the poles are in the LHP, right? So let's solve this. Let's solve this question. I'll tell you how to solve such questions. So sometimes you just have to eliminate the options. That also works sometimes. But still the procedure remains the same. So you're given a differential equation y double dot plus 4y of t equal to ut. So I told you to check the poles. For poles, you need a transfer function. For transfer function, to get a transfer function from the differential equation, you need Laplace transform. So when we talk of transfer functions, we don't talk of initial conditions. So the Laplace transform will be s square ys 4 into ys 4 into sys equal to us. Us is the input, right? Don't confuse it with the step input. So, the Laplace, so the transfer function is g of s, which is equal to y of s over u of s, is equal to 1 divided by s squared plus 4. Okay, so this is our transfer function. Now let's find the poles. Let's find the poles. The poles are s squared plus 4, the roots of this denominator. It means my s squared is equal to minus 4. It implies my s is plus minus 2j. So my poles are plus minus 2j. It means sigma j omega. It means my poles are here and here. This is 2j. This is 2 minus 2j. So one thing is clear. One thing is clear that first tell me this thing. Will the system be BIBO stable? Anybody? Will this system be BIBO stable?
No, sir.
Why?
Sir, because the poles are on imaginary axis and they are repeated.
No, they are not repeated. They're
Uh,
complex conjugate of each other. They are not repeated. If they would have been repeated, then it will be 2j, 2j, and minus 2j, minus 2j, something like that. We'll also see the case. See, for the system to be BIBO stable, the poles should be on the left half plane, strictly on the left half plane. The imaginary axis is also not considered in that case. The poles should be strictly in the left half plane. But in this case, the poles are on the imaginary axis. The system is not unstable as of now, because the definition which we studied in terms of poles, the poles are on the imaginary axis, the system is marginally stable. But is it BIBO stable as well, which we have to choose? What is BIBO stable? You will give some input and you will get some output. So if you give a bounded input and you get an unbounded output, so if you give a bounded input and you get an unbounded output, then your system is not BIBO stable. Now see, this is output, this is input. So you need to give the values of this input. So it means my ys is equal to 1 divided by s square plus 4 into u of s. See, so it means when my system is not BIBO stable, it means then at that case, my system output will be unbounded, right? When my system output will be unbounded, it means my system will become unstable. So when I give some input, the only time I will get an unbounded output response is that my system will become unstable. So now tell me, when can this system be unstable? When can this system become unstable? So see, this is s square plus 4. If you get, so the poles are on 2j and minus 2j. So if you put something, if you put this input in such a way that the contribution of this input gives me the poles of 2j and minus 2j, then I will get repeated poles. I will get even only one 2j if I get, then I'll get repeated poles on the origin, then my system will be unstable, right? So is it possible? Is it possible I'll get something in the denominator like this? Is it possible that the contribution of US is something, I don't care with the numerator, but something in the denominator, which is S square plus 4, or in simple words, S square plus 2 square, right? Why? If I see, then this, what will this system be? Then in that case, this will be S square plus 4 into 1 divided by S square plus 4. What are the roots? The roots will be S is plus minus 2j, and because of this S also plus minus 2j, then I'll get 2 plus I will get root at 2j twice and minus 2j twice. I'll get repeated poles at the origin and my system will be unbounded. So for that input, which has this contribution, my system will be unbounded. Now see how I can obtain this. Check the options. This is valid from the options, but also you can think yourself. See, what is the Laplace transform of sine t or sine of at? The Laplace transform of sine of at is a divided by s square plus a square. Similarly, cos of at is s divided by a square s square plus a square. So if I write something like this, sine of 2t or cos of 2t, what I will get? I will get, for if it is sine of 2t, I will get Laplace transform will be equal to 2 divided by s square plus 2 square. That's what I want. So if my input, similarly, if it is cos 2t, I'll get s divided by s square plus 2 square. So if my input u of t, if it is sine of 2t or cos of 2t, then I'll get the contribution, then the poles will become repeated. And when the poles are repeated at the imaginary axis, my system becomes unstable. When my system is unstable, that means my output in that case will be unbounded. So from the options, we can see only sine 2t fits the answer. It means sine 2t is the correct answer. If you put all other options, you will see you will not get the repeated poles at any of these inputs, right? This is one answer. Now see, can you tell me what will happen if you put cos of 40? So cos of 40, it will be s divided by s square plus 4 square, correct? Now let's try to see the effect of this. So we have 1 divided by s square plus 4, or I'll write it like this, s square by 2 square. And if I take cos 40 as the input, then the effect will be s square plus 4 square. The roots from this is plus minus 2j, and the roots from this is plus minus 4j. Okay, nothing happens because system is still marginally stable. So the pole will be somewhere here, plus 4j and minus 4j, something here, still no repetition. But when you take sine 2t, you get the same poles, the poles become repeated, then the system becomes system output will be unbounded for that input, and we will get an unstable system. Is it understood? If anybody has any questions, please tell me. Otherwise, it will also be cleared in the other. We have 3-4 questions still left. So can you tell me if anybody has any doubt in this? Okay. So basically, there are many ways we can interpret this, and I feel this is the simplest one. Why? Because you'll also be using this concept when we will study Raud-Howitz criteria. So there I'll also utilize this concept. That's why I introduced this beforehand. So basically, you have to see the effect of input in terms of repeated poles at on the imaginary axis. That only makes system unstable, and which means the response is unbounded. Now see this question. Again, similar question. Consider the system whose governing equation is y double dot of t plus 2y dot of t is equal to ut. Now the question is asking the input for which the system output would be unbounded. So again, see, the output will be unbounded. It means the system when does at what making use of which input makes the system unstable. So system is unstable when either because see, if you have these questions and they're asking when the system becomes unbounded, it means the system is not eventually, we cannot directly say whether that is unstable or not, unbounded or not by just looking at it. That's why we have to figure it out. Otherwise, if you have a pole in the right half plane, then for every input, my system output is unbounded. But in these cases, the cases are actually marginally stable. You give some input, you get some output. The output is oscillatory or something, but finite. And because the system is marginally stable, because the poles are at the imaginary axis. But if the poles are at imaginary axis and we are being asked to find whether the system is unbounded or not, then what you have to do, you have to see at which, by applying which input, I get repeated poles at the origin, at the imaginary axis. That solves your problem because when you have repeated poles on the imaginary axis, your system becomes unstable. Now let's take I'll directly write the transfer function. You'll just take the Laplace transform and then take input and output on one side. So we have y of s over u of s, that is equal to 1 divided by s squared plus 2s, or I can write it like this, 1 divided by s into s plus 2. Now what are the poles? Pole location, s is equal to 0 and s is equal to minus 2. So my pole location is like this. Sigma j omega. So my poles are at 0 and at minus 2. Now I'll see by applying which input I get an extra pole at 0. Because here I have one pole which is on the imaginary axis, which is actually at the 0. So by applying which input I get my another pole at 0, that makes my repeated poles at j omega axis, which eventually makes my system unstable, right? Now see, I'll see the output. My output is 1 divided by s into s plus 2 into u of s. So if you take u of s as step input, so what you will get? You will get 1 divided by s into 1 by s. Step is 1 by s and s plus 2. Now what will be the poles? The poles will be 0, 0 and minus 2. So by adding a step input, you introduce repetition on the imaginary axis. That means by using a step input, your system becomes unstable, which means you gave a bounded input, but you got the unbounded output. Because unstable means the response will go to infinity. It means the system will become unbounded because of the repetition at s equal to 0. So it means the answer is 1. Because everything is in time domain here. Let's say 1 because 1 in s domain is 1 by s. Okay. I hope now it is a bit more clear. So if it is clear, then please solve this question. Similar question. I want answers from all. Just write the transfer function based on this. See, it's 4 times differentiation. So it will be something like this. S for xs, we don't care about, sorry, ys. We don't care about initial conditions. Otherwise, it was very difficult to solve. 4 into s square of 4 into s square ys is equal to, sorry, plus 4 into ys equal to us. I'll just write transfer function for you and you tell me the answer when the system output will be unbounded. So the transfer function is g of s, it is equal to 1 divided by s square, sorry, 1 divided by S4 plus 4S squared plus 4, which is also written like this, S squared plus 2 whole square. So you write it like this. Now tell me, this G of S is Y of S over U of S is equal to this. Now the poles are S is equal to plus minus root 2j plus minus root 2j, because you have S to the power 4. So you can also write it like this. If you're confused, S squared plus 2, S squared plus 2. The poles corresponding to this will be plus minus root 2j. Similarly, corresponding to this, plus minus root 2j. Let me plot the roots. Let me plot the roots, sigma j omega. The roots are here and here, again here and here. Now tell me, by looking at the options, what will be the correct option? Anyone? See, you have already repeated poles. You already have repeated poles at the origin. The system is already unstable. So you give any input, the output will be unstable. The input will not make it stable. Right? So you give any input, since there is a repetition on the imaginary axis, the system will be unstable for whatever input you give. So the answer is any bounded input. Anybody has any doubt here? If that is not the case, please solve this question. I want answers. I want answers from you. You have? Oh, sorry, there is an answer written. Okay, now tell me. Tell me the answer. I'll just make it simple for you guys. So I'll write my y of s over u of s is equal to g of s is equal to 1 divided by s squared minus s minus 2. So if I simplify it a bit, it will be 1 divided by s plus 1 into s minus 2. So the poles are, my poles are at s equal to minus 1 and s equal to plus 2. If I plot them, sigma j omega, my pole is at plus 2 and minus 1. So whenever you are solving such questions, first make sure that you plot the poles and decide from the pole locations whether your system is stable or not. See, in this case, it's unstable because one of the poles is in the right half plane. So whatever input you give, the system will always be unstable. So see, if you give any bounded input, still the system will be unstable. Why? The output will be unbounded because this is an unstable system. So you only need to think of making the poles repeated or something like that if the poles are on the imaginary axis, right? So there is, if you give any input, the system output will be unbounded because the system is an unstable system. If anybody has any question, please tell me, or we will just solve the last question of the day, because that's all you have in your assignment. You have some transfer function questions. You have some, okay, I skipped a few questions which are based on finding poles and zeros. I think they're very, very simple. We just need to solve quadratic equation, cubic equation, or whatever. And that's like anybody can do that. You just have to evaluate quadratic equations. So, but you have, I think, 2, 3 questions based on this, when a system is stable or BIBO stable in general. And you have a questions where you are asked to find the transfer function, very simple questions. Yeah, but you have 3, 4 questions as I discussed on BIBO stability. So that's it. I think it's not that difficult. This assignment, just questions on BIBO stability and transfer function. Others are very simple. Now, if you have understood this question, whatever you've learned in the previous week and this week, it combines both. And if you're able to answer this, I have not given any option. If you're able to answer this, it means you have understood the concept, or then there is no need to go through again the contents of your week, etc. and etc. But if you're not able to solve it, then something is wrong, and you need to look into your notes or revise concepts, etc. and etc. Right? So if you're able to solve this question, then that means you will be able to solve similar questions in GATE or other competitive exams. But some of you who joined late, I just explained one thing, which is, I'll just explain this question first. See, an LTI system with simple poles at s equal to -2 and s equal to -4 and one simple zero at s equal to -1. So you are given an LTI system with simple poles. Simple poles means there is no repetition, there is no coincidence, right? So there is no repetition of poles. If it is simple pole at -2, it means there is only one pole at -2, right? So you are given a system with 2 poles and a zero. Then it's asked, it's given in the question, a unit step is applied, and at steady state, the output has a constant value of 1. Correct? See, so, and we have to find the impulse response. I told you in the beginning. See, what is impulse response? See, what is step response? If you give input as ut to your system, then the output is called, so if you give step input, the output is called step response. Why? Because your input is a step signal. So if you are giving input as a step input, then your output is called step response. If you are giving output as a ramp signal, RT, your response is called ramp response. Similarly, if you are giving parabolic input as the input, parabolic like function as the input, then the output response you get is called parabolic response. Similarly, if you are giving an impulse signal as input, the output is called impulse response. I'll not go into the details of this, but I'll just tell you one point which might be evident from your notes or from your lectures. You'll have to figure it out, but I'll just tell you one thing. I told you transfer function is a Laplace transform of output to the input with 0 initial conditions, but there is another definition that which says a transfer function is the Laplace transform of impulse response. See, this impulse response it's denoted by ht. So it's in time domain. Transfer function is in s domain. So if you have ht, and if you take a Laplace transform of this, you will get h of s. This h of s is transfer function. So if you are given a transfer function, you take inverse Laplace of this, you will get impulse response. So remember this point. Whenever the question is asking you to find the impulse response, it means you have a transfer function. You need to take inverse Laplace, then you will get the impulse response. Or if you're asked to find the transfer function and there is nothing visible, only impulse response sort of thing is visible, then you have to take the Laplace transform of that and you will get the transfer function. Now let's look into the question. Question is, you're given some transfer function. There are actually two concepts which are mixed in. There is a concept of final value theorem also in the question. See, now let's come to the question. You're given, you have a system, G of S, or it's actually given. So you have a pole, you have a system with one simple pole at one simple zero at -1. So it will be S plus 1 because 0 is at -1. So zeros are in the numerator. Then you have two poles, two simple poles at -2 and -4. It means your denominator is something like this, S plus 2 and S plus 4. So I think that was given. Yeah, -2 and -4. So your system is somehow given like this, but there is not proper, it's not directly given that your system is this. I'm just assuming based on the information I have. But there is some constant normally here, some constant K, which is normally multiplied. If you have seen some questions, you have something 10 into S plus 1 divided by S plus 2 into S plus 4. Since I do not have the complete system information, I need to assume this K to be unknown. I don't know this because there is nothing given directly to it. But yeah, there has to be this K when you write a transfer function. Now, how you will evaluate this K? You can evaluate this if you somehow know the value of this GS, right? What is this GS? GS is YS over US is equal to K into S plus 1 divided by S plus 2 into S plus 4. Now see, let's make use of this thing. A unit step is applied, and at steady state, the output has a constant value of 1. So unit step is applied, it means U of S is 1 by S. So U of S is 1 by S. And at steady state, it means Y at infinity, the value is 1. It means the final value of Y is 1. Right? So you need to apply. So how you can find this final value? You can just take the inverse Laplace transform of your transfer function. You'll get something in time domain, then put t equal to infinity and you will get y infinity. But why would you do that? Because you know a final value theorem. So if you're given a transfer function, you can apply final value theorem and get the values. But the only condition is final value theorem should be applicable. So the conditions for final value theorem to be applicable is the system should be bounded, right? The system should be bounded. It means the poles should be in the left half plane. And that is the case. We have poles, two poles at -2 and -4. It means they're already in the left half plane. The system is bounded. It means we can apply the final value theorem. Other conditions, the system has to be proper. That means the degree of numerator has to be less than the degree of denominator, which is the case and which will be the case most of the times. The denominator degree will be less than the degree of this denominator. Numerator will be less than the degree of denominator. You will study that, why that is the case after some weeks. So let's come to the question. So we have y of s after putting in 1 by s, I'll get something like this, k into s plus 1. When I put u as 1 by s, so I'll get s into s plus 2 into s plus 4. So now here I can apply the final value theorem. But again, check whether I can apply the final value theorem or not. The condition is the root should be on the left half plane with at most one pole at the origin, one root at the origin. So that is the case here. Even if the poles are not strictly on the left half plane, but you have one pole at the origin, that's still acceptable. So that is the case here. So you have s equal to 0, one pole at the origin and the other pole at -2 and -4. So final value theorem can be applied. Okay, Let's apply. Let's apply final value theorem. So final value theorem says the final value, which is in this case given as 1. So my 1 is equal to limiting s tends to 0, s into f of x, s into k into s plus 1 divided by s into s plus 2 into s plus 4. This s and this s goes put in the limit as 0. It means you get this 1 is equal to k divided by 4 twos are 8. It implies your k is equal to 8. Now you got the value of k from applying the final value theorem. So it means your g of s is what? 8 into s plus 1 divided by s plus 2 into s plus 4. Now what you have to find? What you have to find? Impulse response, right? And what is impulse response? I told you impulse response, if transfer function is given, if you have to find impulse response ht, just take inverse Laplace. And if inverse impulse response is given, you need to find the transfer function. Just take Laplace transform. You're done. So when you take the inverse Laplace of this thing, you need to apply partial fraction. So this is a very good question. Why? Because it involves all the concepts which you have learned in these 2 weeks. So try similar questions. See previous year gate questions after you are done with this class. See previous year gate questions and try. There will be similar questions based on this. So try solving them. If you're able to solve them, then you have learned the concepts, because in gate, they'll not give you a question only on initial value theorem or only on state space or only on transfer function. They will give you a mixed question which combines which combines the content of, for example, this course, 3-4 weeks course, and you are done. Right? So when you solve this from partial fractions, you find the value of this as in terms of this, and how you will find the impulse response h of t by just taking the inverse Laplace, which will be 4 e raised to the power minus 2t plus 12 e raised to the power minus 4t. Okay, so that's it. That's the answer. That's the impulse response. I have not given the questions. I have not mentioned the options. So you just solve with this thing at your home. Partial fractions, maybe there is some mistake because I directly wrote it. So you just write this partial fraction in detail and then take inverse Laplace from this partial fraction, you get the impulse response. Now try to see questions where you are given an impulse response and you have to find the transfer function. The concepts, there will be other concepts as well. Initial value theorem, final value theorem, some trick will be there as we saw in some of the questions today. So this is it. I think if you're able to solve these questions, then if you have understood this all, then I think you can easily solve all your assignment questions. Like they are not difficult, but one thing which I assume is you regularly go through your lecture notes. Because I do not teach here, I just assume you know transfer function, I assume you know impulse response. My task is to just help you with the assignment, not with the concepts in detail. I cannot do that in 2 hours. Right, so with this, we end today's lecture. If anybody has any question or any doubt in any of the questions that we discussed today, you can unmute yourself and ask. If you have any doubt, whatever we have covered today, so feel free to ask. Otherwise, I think we have covered sufficient number of questions. We did some 11 questions, and just recap. I'll just recap what we did today. We started with transfer function questions where we had given questions where we were given differential equations and we were asked to find the transfer function. One way is to just take Laplace, then find a relationship of output over input assuming zero initial conditions. That's your transfer function questions. Other questions where you were given a model where you have to derive using basic physics, basic laws of motion or equations or whatever is governing that model. Use those equations. If it's a circuit, there will be KCL and KVL. If it's a spring mass damper, there will be Newton's laws, right? Similarly, other things, you just apply them, get the relationship of input or output or input, you get a differential equation, solve that. Again, in terms of you have a differential equation which is in time domain, take Laplace, get it S domain, find the relationship, you're done. Then at the last, we have some questions related to bounded input, bounded output stability, where you're given, where you have to see when my system is stable. First of all, you look into the pole locations and say, okay, my system is stable when my poles are in the right left up plane. And if that is not the case, then you have to see if your poles are on the imaginary axis, then you see, okay, when my poles become repeated on imaginary axis, then your system becomes unstable, and that's the case when your bounded input concept fails. That's it. With this in hand, I think you should be able to solve all of the assignment questions. They're not difficult. Try to practice some gate level questions because as I told you in the beginning as well, that this is a basic control systems course. You have to work hard if you're preparing for gate with this course. By taking this course, we are preparing for gate. Mere registering in this course will not work. You yourself have to work hard. And since there is no two-way interaction with the instructor, so you will have to work yourself. Be honest to yourself and attend all the problem solving sessions or attend any of the problem solving sessions and make sure you're able to solve all the assignment questions, and that's it. If you're able to solve all your assignment based questions, just seeing one problem solving lecture, you're done. No need to see other lectures because if you're able to solve all the assignment questions, it means you have understood the contents well and try some gate level questions. If you're also able to solve them, then that means you have understood well and you can proceed. These are, and one more thing, these are a bit, as of now, these are starting weeks, so you cannot expect the assignments to be tough. But as we proceed, you will see when root locus comes in to picture and Bode plot, Nyquist plot, and other things, when they come into picture, you will see things building up and becoming difficult and actually relating to what happens in the gate or what appears in the gate exam. And your last exam, which will enable you to get the certificate from this course, and how how your exam will be conducted. That will be similar to gate exam. You have an online computer-based exam where there are some questions, 50 or 60. There is no derivation, nothing, just numericals. There are multiple choice questions. There are blank. There are questions where you are given a range. There are multiple answer questions as well, multiple select questions, or fill in the blanks. There are sort of questions similar to that. So you have to prepare like that. So make sure you're able to solve assignments, because final exam will be something similar to what happens in what is there in the assignments. Okay, now anybody has any question? I told you last time as well. Practice from some books, practice from internet, practice using previous year gate books, previous year questions of the gate of other competitive exams, and then you're good to go. Anybody has any question? Otherwise, we can just stop the recording. Thank you very much for attending this session.